Hi, welcome to Earth Science. In this introductory lecture, we will simply be discussing what is Earth science, what are the main physical components of our planet, and we'll also take a look into how those different components that make up the planet interact with each other and change each other, because that is really the theme of this entire course. So, let's get started. Earth science is really the name for all of the different groups of science that deal with Earth and also Earth's neighbors in space, the moon, other planets, and stars. So it's a collection of many different disciplines, including geology. Most of this course is a geology course where we study the solid body of the Earth, and this takes us to plate tectonics, minerals and rocks, the rock cycle, earthquakes, volcanoes, many things. Then there's oceanography, which is the study of ocean currents, the life in the oceans, the chemistry of it, how oceans affect the climate, and many other things. Meteorology, which is the study of weather and climate as well, and the processes that shape it. And then finally, there is astronomy, which is the study of the universe. Earth is a celestial object in and of itself. How it got here, the planet, we can see that evidence out there in the universe. And there are things in the universe that influence and affect Earth as well. So we will study astronomy also, which takes us beyond Earth in this course. So the planet, in a nutshell, really just basics, boil it down to the absolute essentials here. Earth is divided really into these three different physical environments. One is the hydrosphere. So this is all of the water on our planet, liquid and frozen. And sometimes the frozen portion of our planet is referred to as the cryosphere. So this would be continental ice sheets, such as in Antarctica and Greenland, and also the sea ice, which borders around Antarctica and then around the Arctic Circle as well. 97% of the hydrosphere is contained within the oceans, and then with the little bit of fresh water that's available, the vast majority of it is really, well, actually unavailable, at least for us. So here's the breakdown of that small percentage of fresh water. 2/3 of it is frozen, and almost the rest of it is under the ground. And we can get to a lot of that water, but all of the surface water that we have access to represents a really small amount, as a matter of fact. Next, there is the atmosphere. This is just a thin blanket of air that blankets our planet, and it maintains and sustains life. Besides just the oxygen for us to breathe and carbon dioxide for plants to absorb, it also shields us from harmful UV radiation. It traps warmth. It reflects too much warmth, and maintains a balance on our planet. Our closest neighbor in space is the moon, just as far away from the sun as we are, but the moon has no atmosphere whatsoever. So on the lit portions, the daytime sides of the moon, temperatures soar up to around 100 degrees Celsius, north of 100 degrees Celsius, getting up to around 250 degrees Fahrenheit. Whereas on the dark side of the moon, because there's no thermal insulation, there's no way to trap warmth, you're basically exposed to the naked vacuum of outer space, and temperatures plummet to around negative 200 degrees Fahrenheit. Off the top of my head, I don't know what that is in Celsius. I think it's around negative 70. So the extent of the atmosphere is it goes really about 100 kilometers into space, but the vast majority of all the molecules of our atmosphere, thanks to gravity, are pulled down very close to the Earth. So about 90% of the atmospheric molecules are concentrated in the bottom, 16% in this case. And then the atmosphere is extremely dynamic. The energy that is absorbed and contained within the atmosphere is what produces weather and climate and can release unbelievable amounts of energy. A typical thundercloud has many times the energy of a small nuclear bomb, and a hurricane will release vast amounts of energy. I don't know exactly, but perhaps equivalent to the total amount of energy for electricity that an entire country consumes over the course of a year. And it's, I sort of said this, but it's by far the part of our planet that changes the most frequently, the most rapidly over time. And this is what the atmosphere looks like from outer space, if you've never seen it before. In terms of composition, it's the majority of it is nitrogen, which only very specialized bacteria on our planet can actually absorb and do anything with. We just breathe it right out. Plants they absorb it, but nothing really happens chemically with it. And it's about 21% oxygen and about 1% argon, which is an inert gas that really doesn't react. As far as what's left, a very small amount, carbon dioxide makes up the majority of that. So there is our greenhouse gas. We need carbon dioxide, otherwise our planet would be far too cold for life as we know it really to exist and continue. But too much carbon dioxide is also a problem. The bulk of the Earth, the geosphere, that's just the solid sphere of our planet. You compare, again, our closest celestial neighbor, the moon really just is a geosphere. There's nothing else to it. So if we get rid of all air, water, and life on our planet, we're just a geosphere. The geosphere, though, it's layered, kind of like an onion. It has these different layers, went too far, sorry, which you probably know about. The crust, mantle, and the core. We can break those down a little further into lithosphere, asthenosphere, mesosphere, outer core, and inner core, which eventually we will do in this class. So there's a preview of the interior of our planet. And the planet is, I know that you know planet Earth is huge, but you really have no idea just how big it is. The tallest mountain on our planet, Mount Everest, is about 8 kilometers tall. The deepest point in the ocean, the Mariana Trench, that is around 17 kilometers deep, if memory serves me correctly. But the planet, the radius of our planet is well over 6,000 kilometers deep. So the tallest mountain to us, which seems like such an exaggerated feature, in the grand scheme of things, compared to the rest of the geosphere, is really nothing at all. If we could make Earth the size of an actual globe and you felt its surface, it would feel just as smooth as a bowling ball does. In terms of composition, most of the physical planet is actually iron, a whopping 35%. Almost all of it is located in the core. However, iron is also very common in Earth's crust as well. Oxygen is the next most common element on our planet, followed by, well, you can see the list here. On the surface of the geosphere, the more common elements are a lot different. Oxygen, as you can see, is the most common, followed by silicon. Aluminum, iron and magnesium, I think, are really high up there as well, part of the top 5. So the geosphere is dynamic too. It's just dynamic on extremely slow scales, and the crust and mantle really are the parts that drive what's going on the surface. And then as well, the plates move around and they lift up and they pull apart. But then weathering and erosion, which are more atmospheric, hydrospheric processes, well, they change and sculpt the geosphere on the surface, obviously. The part of Earth on top that moves around is known as the lithosphere, and that includes the crust plus a little bit of the mantle, and the very top portion of the mantle is called the asthenosphere, which is sort of similar to magma or lava, and that is sort of what the lithosphere glides or moves over very, very, very slowly. And the parts of the asthenosphere come up to the surface in the form of lava. So Earth is broken up into these tectonic plates. Here we can see a diagram that illustrates a little bit how those move around, which we'll get into the details on all of this eventually. And then this really isn't a physical environment, but there is a biosphere on Earth too. If you look at Earth from outer space, vast, enormous swaths of it are green, and that green is life. So the biosphere extends to the bottom of the ocean, onto the surface, and even places cut off from the outside world inside of caves and things like that. There are countless interactions that living things have with the atmosphere, with the rest of the biosphere, with the geosphere and the hydrosphere. Now, humans are part of the biosphere, but we treat human activity as a completely separate field of study, we will highlight it multiple times as often as we can all throughout this course, because we have a big impact on our planet. So part 2 here, we are going to look at what's called Earth System Science. So the reason we do this, the reason we have this, is because our planet has all these different spheres to it, but they all, at some level, interact with each other, and they cause changes. So this is what's known as Earth System Sciences. If you want to try to understand our planet, or even one part of our planet, you still have to know how that part of the planet is affected by other parts of the planet as well. So here's just a really general example that I give in class. This is the Arctic Ocean, and under the ice we can see this kind of yellowish, greenish, brownish looking stuff. Well, that is algae that grows on the bottom of the ice. There's no soil, there's no real surfaces for plants to grow on, but they do cling to the bottom of the ice. And there are tiny organisms called krill which eat that. That is basically their only form of sustenance. Now, larger communities of organisms eat these krill, and then other organisms eat the ones that eat them. Whales, baleen whales like the blue whale, the largest animal that's ever existed, eats almost exclusively this kind of organism. Okay, so we have the hydrosphere, well, the cryosphere part of the hydrosphere, and the biosphere interacting here. Well, also, so why should we care? Well, this is being influenced by other things. The atmosphere is being warmed by human activity, and that warming of the atmosphere warms the hydrosphere, and it causes portions of the cryosphere to shrink, which means there are fewer of those organisms, which means there's less food for other types of organisms. So we didn't really include the geosphere here, but we have human activity, the rest of the biosphere, the atmosphere, and the hydrosphere all interconnected on this one basic thing. Of course, that is just one example. There are countless examples which we will get to in the course of learning. So let's define a system. A system is any size group of interacting parts that form a complex whole. So what systems really do, what a system is it's a mechanism of parts, or however you want to put it, but it transfers matter and energy from one place to another. And basically everything is some sort of system. Nothing just sits and exists on its own and doesn't do anything or is not changed by other things. The two main types of systems: closed systems, no material comes in or out of them. Everything is recycled in terms of matter, and the source of energy, the source for energy, is self-contained. So a cell phone is a pretty decent example of a closed system. It stores its own internal energy. Yeah, you have to recharge it, but you're not actually adding material to your phone to do that. You're just changing the battery inside of it. You're moving the electrons in the battery around. And so everything that it needs to do is self-contained. Whereas open systems can't work unless matter and energy are constantly introduced to them. So a car is a great example of an open system. It only works if it's a internal combustion car. It has to take air from the environment to mix it with the fuel to burn it, and it also requires that fuel to be added to it. It can only go as long as it has fuel within the thing. So that's what makes it an open system. And Earth is actually both an open and a closed system. The gist of it is the geosphere and the processes that go on with the geosphere are closed system interactions. Meanwhile, all other spheres are open system interactions. So a system can't work unless there's energy. The definition of energy is the capacity to do work. So, and work, we can maybe rephrase that as the ability to cause change. So, what are these sources? Well, for the sun is what makes the Earth, gives the Earth open system components. So processes such as the weather and climate, erosion, and life. And along with that, we would include ocean currents and things like that. Not ocean tides, that's caused by gravity, but ocean currents, certainly without wind, without differences in heating to make those ocean currents move around. All of those things would completely stop. And then Earth's interior, the heat locked within our planet, which causes the interior of the geosphere to move and mix and convect around, which drives plate tectonics, including earthquakes, volcanoes, and all that, is the other source of energy. So here we have, this is not Earth. This is Mars. Now, Mars is basically, for the most part, just a geosphere. Mars has a cryosphere. There's actually quite a lot of frozen water on Mars, but that frozen water, for the most part, doesn't really change or interact. Sometimes a little bit of it melts and evaporates. Mars does have an atmosphere, but it's so incredibly thin that it really doesn't cause change on any noticeable scale on the planet. And then there's no life on Mars. But Mars used to be very, very dynamic. We can see here from this topographical map of the planet that those are volcanoes, those sort of white dots on the surface. So it used to have an active geosphere. This red bulge, it's called the Tharsis bulge, and it has a great tear through it called the Valles Marineris, probably a rift. So the geosphere used to be dynamic and moving around, and it brought material up to the surface. That's why those volcanoes exist. If we peer closer, not really closer, but if we get a little more detail here, we can see that extending out of Valles Marineris, these blue regions, those are the telltale signs of enormous rivers that used to be on the planet. So there used to be an ocean that covered almost the entire northern hemisphere of Mars, and so it had weather. It had a water cycle. Maybe it had life at one point, but it doesn't anymore because it's sort of lost on the interior. It lost its source of energy because the interior of the planet cooled down to the point where it couldn't mix and move around anymore. So the volcanoes are all extinct. They have not erupted for billions of years, likely. With that, it lost its magnetic field, so its atmosphere and hydrosphere were removed by the solar winds and all of that kind of stuff. But on Earth, we are lucky enough to be an active, dynamic planet with all these kinds of things happening. So basically on Mars, there really aren't any open or closed systems going on anymore. But an environment like Mars, so environments that look similar to this on Earth, are transformed because there is an active water cycle and because there's active weather and because there is life. Barren rocks, just naked geosphere, can be slowly transformed into extremely productive and dynamic ecosystems. Getting back to humans here, so we play a very significant role. Every single part of the planet is influenced by human activity. I would say we have the least influence over the geosphere. It's hard to say which one we have the most influence over. Probably the biosphere, and then I would perhaps argue that the hydrosphere is the one, we affect that more directly than the atmosphere, actually. So, examples of what we do to cause changes: we pollute because we emit and we create plastics and emissions, which contributes to global warming. We take non-renewable resources out of our environment. We also cause species to go extinct on massive scales. So the environment, that is everything that surrounds and influences a living thing. It includes other organisms, other living things, but it also includes the physical aspects of the environment, which include water, soil, sunlight, and the weather. Now, so far, humans don't have a direct impact on the sun, We haven't figured out a way to manipulate the sun. But we do have good reason to think that the weather is different on the planet because of us, and the climate is different. And the water, the air, and the soil, we know for a fact, are different because of human activity. And I already mentioned the living biotic factors. So environmental science is the study of how humans interact with the planet, with their environment. The study of the environment itself is ecology. We will be more focused on environmental science when it's relevant to what we're studying. So there is this idea that some people have that we could or should terraform other planets, such as Mars. So we take Mars as it is on the left, and the idea is we transform it to what you see on the right by giving it an atmosphere, by melting the ice that's on the planet so it can have liquid water, and then eventually life. But terraforming is looked at as, is that even possible? And then it's also looked at as, well, if it is possible, why would we go and do it with Mars? Well, in reality, we have already terraformed. So this is a portion of the Midwest, kind of near where I'm from originally, in South Dakota. And the land looks really bizarre and pixelated, but that's because the land has been terraformed. Almost everything you see here is farmland. So the top of the soil, the original soil, has been ripped up, the grasses and plants, and it's been replaced by non-native plants. Everything in this picture should be a fairly uniform deep green, but we've totally disrupted that, and we are looking at hundreds and thousands of square miles just in this picture. But this is actually a pretty narrow, pretty zoomed in look at it. We could retake this picture hundreds of times over the surface of just this country, but then the rest of the world too. If we zoom out a little further, we can see cities. We have the city of Minneapolis towards the top right corner, or the Twin Cities of Minneapolis, St. Paul, towards the top right-hand corner here. Even though, human beings, there are a lot of us, 7.5 billion, you could pretty comfortably fit every single human being in an area just a little bit bigger than Rhode Island. Now, I said comfortably. No, nobody would be comfortable, but we would fit. Everybody would get like a square meter of space. So in total, we're this very small component on our planet, but because of the power we possess through technology, we have completely transformed the surface of this planet. We've completely transformed many of the surfaces of this planet. Here in the Amazon, we can see much of it is still naked rainforest that hasn't been touched, but sort of in the bottom right-hand quadrant of this, that has all been, again, you can kind of see that it's been altered. It's been ripped up. It looks pixelated. You can see where ribbons of human activity have gone into the rainforest and cut materials out of there and removed them. This is in Utah, so there's an entire mountain that has been excavated away to mine for its copper. This is one of the more dramatic ones. This is in New Zealand, and that's a volcano in the middle, obviously. But there's a forest that exists around it. But the entire region used to be that same dark green and been covered in trees. But instead, it's all farmland and towns and things like that. So perhaps a few billion trees were cut down from this area. Maybe not billion, probably closer to a couple, several tens of millions. But that is a huge, and again, this is just a tiny corner of the world. That is a huge impact, and we've multiplied this all over our planet. And because of all that progress, obviously it leads to a lot of pollution, and we've messed with the atmosphere as well. We will get more in depth on that stuff later on. So, but going forward in this class, yes, we will be talking about all of the bad things that our activity does, but I want a better world for myself, for future generations, and for other people that are not as fortunate as me on this planet. And the only way, and I also want the planet itself to be in a good place. The only way that that can be possible, where everybody and everything can win, is with better technology. Not by going backwards, not by trying to take what humans do and do less. For example, the only way to get away from fossil fuels is to use them to build better technology. We can't just say, starting today, we just no longer will use them, because that would be a death sentence for billions of people around the world, as the way things currently sit, it would be. The only way to clean up our pollution will be to make even more stuff that will be used to clean it. The only way to improve our health and longevity is through technology. So the perspective I want us to have going forward is, how do we accept responsibility and do the right thing while maintaining our own success? Those are things I want us to always keep in mind. And that does it for this first introductory lecture. Thank you for watching.